Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 34, Custom Geometries and Materials. In the previous videos, you've learned how to create a large number of standard geometric shapes, like planes and spheres and cylinders. But what if you want to create a non-standard shape? In this video, you're going to learn how to extend the geometry class within an application to create some customized shapes. And we'll also do a couple of examples where we learn how to create customized materials to give objects a special unique effect in an application. Our first example is going to be creating this shape. So you can see it's kind of shaped like two mountains or kind of an M. And this is not something we can do with, say, the polygon geometry class. So we're going to create a new application and just create this in code. So let's start off by going to our development environment using Sublime Text. I'm going to start off by going to the test template file. This is a great way to get started quickly. We created this previously by copying some code from another example. It contains the core classes that we're going to need in every scene: base, renderer, scene, camera, and mesh, and two sample classes we could use to render a shape. In this case, box geometry and surface basic material. So in the template file, I'm going to add a couple more lines of code because these are going to be useful in the 4 examples we'll be working on in this video. So first I'll say from geometry.geometry, the geometry file, import the capital G geometry class. And later on when we do custom materials, we'll say from material.material import capital M, the class material. I'm going to save those changes to the template file and make a new example. So let's see, this will be in our root folder, and this video, let's see, we'll make this number, this will be test34.py. In fact, let's make this test34a. We'll call this 34, we'll just call the next one B. All right, I'm going to start off by copying the code from test template. So Control A to select all, Control C to copy, Control V to paste. And this class will just render the front face of a cube. Not too exciting. So we're going to replace some of this code. Specifically, instead of using this pre-built geometry, we're going to make our own extension. So let's go ahead and say make a new geometry object. It's very strange to initialize a geometry like this. We need to go through the same tasks that we have before. So we need to load in some vertex position data, some vertex color data, and then we need to upload the data from the attributes. So to build this particular example, before we do something like this, we might want to think about how many vertices there will be. In this case, maybe 5 vertices. Right, so like 0, 1, 2, 3, and 4. And we'll want to think about how we're going to group these into triangles as well. So I think we can do this with a triangle on the upper left, a similar triangle on the upper right, and a triangle down here. And so we'll use 5 vertices, group that data into 3 triangles. And the vertex colors, we'll use a red for these 2 vertices, a yellow for this vertex, and greens for these 2 vertices down there. So that's the plan. So let's start off by making some points. And so first I'll start off with the top left point. Let's say that's about here. And these will all be in the plane z equals 0. This is going to be a flat object. The next point, let's make that the one that's directly in the center. Next, point 2, that'll be the point in the upper right. 0.1, 0.1, 0.0. Point 3, be negative 0.2, negative 0.2, 0. And 0.4, let's make that 0.2, negative 0.2, 0.0. I don't know why I sometimes used points and sometimes not. All right, now we need to group these into triangles. Right, so we'll make an array called position data, and we'll just group these into sets of 3. So we'll start off with maybe that triangle on the upper left. That'll be P0, P3, P1, followed by, say, the triangle in the middle, P1, P3, P4, followed by the triangle at the end, P1, P4, P2. By the end, I mean the upper right. So it's our position data. And we could immediately say geometry. We're going to add a new attribute. We need to know something about the variable names in the vertex shader we're using. And in this case, we're using surface basic material. So I know that position is stored in a variable called vertex position. And we're just going to put pos data in there. All right, it's coming along nicely. Next, we're going to want some color data. In this case, we're just using 3 colors. So maybe I'll just put them in arrays for simplicity. There's red, yellow is 1, 1, 0, and green, like a nice dark green, 0, 0.2, 0. All right, next, let's group that into color data. Again, I want to be sure to use the colors in the same pattern that I use the positions. So for instance, the top left corner is P0, and I want that to be red. So every place I see a P0, I'm going to put the red color. Same for P2. P2 is one of those top corners that we're going to color red. So when we put it all together, we'll get red, green, yellow. For the leftmost triangle, for the center triangle, yellow, green, green, and for the rightmost triangle, yellow, green, red. Green, red. Okay, now we're going to add this as a new attribute in our geometry. So geometry dot add attribute. That's another vec3. I know the name of the variable is vertex color. We're putting call data in there. Then when you're done, you need to know how many vertices there are. So we'll use the count vertices function. And I think that should be all that we need. Right, we've declared our geometry, given it position data and color data, and that's just what the shader needs to work. And we're using the standard surface basic material. Excellent. So let's go ahead and build this and see how that looks. And there we have it. It's very small because the camera is very far away. Let's move that camera a lot closer. Let's build that one more time so we can see it. Yeah, sure enough, that does look like the image we saw on the slide earlier. And that's how you can quickly create a custom geometry. You need to know your points, your vertices. You need to know how to group them into triangles. And if you're using vertex colors, you need to put that data in too. Now, as we learned when we were creating surfaces, sometimes it's easier to generate data using a function. So for the next example, we're going to learn how to create this shape. Right, these points here are points along a sine wave. And you might notice that I'm actually using 2 materials in this example. We're using both a point material for the yellow points and then a line material to connect the geometric points. So this will also be an example where we reuse the data twice. All right, to implement this, again, we're going to go over to our Sublime text. And in the template file, I'm actually going to add in a couple more imports. Could be handy later, so we'll add them here. Let's add material point basic material. Import the class, so capital P, point basic material. And from material.lineBasicMaterial, let's import the class lineBasicMaterial. All right, let's save the template file. Now we're going to create our second example in this video. So I'm going to right-click the Python graphics folder, make a new file, and call this one test34b.py. I'm going to copy all the code from the test template file into our new example. All right, and we're going to go ahead and create another custom geometry class. So just like before, I'd like to replace box geometry with simply geometry. And we're going to create an array of data. And so position data, I'll start off with an empty array. And then let's see, how could we do this? Let's say for x in range, so this is a little bit tricky. I'd really like decimal values, but what I can do instead is I can say maybe like -32 to +32. Let's go in intervals of 1. Right, I'd really like maybe -pi to pi, but in this case, I'll just divide each of those x values by 10. Right, so in the position data array, I would like to append a point. I'd like to append, let's see, x divided by 10, sine of x divided by 10. I think I'm going to have to import the sine function in a moment, and 0. Before I forget, I'm going to go ahead and import sine from the math package up at the top. So from math, import sine. All right. So that's how I'm going to generate my position data. It's actually a lot shorter if you have a formula for it. Now I can create an attribute based on that. Add attribute vec3 vertex position and put the pos data in there. Now in this case, I'm using a solid color to render these geometry shapes, so I don't really need to generate vertex color data. So the next thing I'll do is I'm going to render this. I'm going to render it twice altogether. First, I'll change the material to surface point material. I don't want to use vertex colors, so I can get rid of that code. But I do want to add a base color. See, and I think the points were rendered in yellow. All right, so the dictionary that I pass in here, I can set the value of the base color uniform using an array with RGB values. All right, so if this goes according to plan, we should see a bunch of points. Let's save that and let's build. Let's see what that looks like. All right, surface point material. Not surface point material, point basic material. Let's try that again. Point basic materials, name of the class. And what else is wrong here? Let's see. Point basic material. Let's see. Render the camera, the draw style. Let's see. Wrong type. Must not have set the right type in this material. Let's see what point basic material looks like. This will be in the material class. GL points, that sounds fine. Point size. Let's think about this for a second. So what is the wrong type? Mesh 0. Well, if it comes after the 0, that means I didn't actually count the vertices in my shape. It has no idea how many to use, so it's probably trying to pass a none type. Let's add count vertices to this example and run it one more time. Oh, and now I need to use consistent tabs and spaces. See, oh, it looks like some places here I've used tabs and some places I've used spaces. So let me go ahead and say, see, within indent using spaces, convert indentation to spaces. Save and give that a run. Third time's the charm. There we go. We've got a set of points right here. I can't see all the points because I'm zoomed in a little bit too much, but that's an easy fix. I can pull the camera out a bit. Maybe pull that out to z equals 7. Save and run that again. See if I can see all those points. Yeah, sure enough, there's a lot of points. They're spaced really closely together. I could space them out by changing my value in this range here. So let me change that to 3. And we'll get every third point in that case. There we go, that's pretty good. Now, to connect the points, we'll just add another mesh, which uses the same geometry, but instead of using a point material, I should name this something better, so I'll call this point material, to distinguish it from what I'm about to do, to create a line material. So this is a line basic material. And here, let's see, the uniform I'd like to set is, once again, base color. Oop, that doesn't go there. That goes here. Base color. This time I think I want a nice magenta, so 101. And self.mesh 2. I need to give these better names. I'm going to use the same geometric data, but using the line material. And let's give these nice names, right? Let's call this one line mesh. No, that's the point one. Let's call that one point mesh. Let's call this one line mesh. And then to the scene, we'll add point mesh and line mesh. And if we just called everything mesh 1, mesh 2, mesh 3, life would get confusing very quickly. All right, so we've generated some geometric data. All right, we've created 2 different meshes using the same geometric data, but different materials with different colors. We've added them both to the scene. So now if we build this one, we should see something resembling, sure enough, that's the picture we saw on the slide. So that's another example of creating a customized geometry, in this case, using a function to generate your data. All right, we're on a roll, so let's keep on going. The next thing I'd like to make, let's see, I've done some custom geometries. Let's do some custom materials too. So what you see here is a sphere. This is actually a sphere of radius 3. And instead of using vertex colors to generate this, I'm actually using the positions of each point, the x, y, and z coordinates, to generate the RGB values. Right, so start off, the red value is controlled by the x coordinate, starting off at 0 and going up to 1. You might notice the sphere becomes redder. And then, once we get to 1, it resets back to 0. I'm taking the fractional part from 0 up to 1, from 0 up to 1. Same thing in the y direction. That's going to control the green component, starting at 0 and going up to 1, becomes fully green. 0, going up to 1, and so forth. And you can't really see it from this perspective, but the z values control the blue component of the color of the sphere. All right, let's see if we can implement this in code. So let's go ahead, close down that example, and let's start a new one. In the core folder, I'm going to make a new file. Let's call this one test34c.py. This will be our first example of a custom material. It's also a good reminder of all the work we put into the material class. All right, so for this example, I'm going to want to use a sphere. So I also want to add from geometry.file sphere geometry import capital S sphere geometry. I've already imported the material class. in this case, I'd like a sphere geometry of radius 3. And I know I'm going to need to pull my camera back. If I left my camera at this position, it would be making contact with the edge of the sphere. So maybe let's pull the camera back to z equals 7. So we get this entire sphere in the scene. And now, instead of using this material, we're just going to create a new material. Right? So to create a material, it's been a while, but you might remember we need to write a vertex shader and a fragment shader. And because of the way the renderer class is set up, it's going to be looking for particular variables, like a model matrix and a view matrix. So we have to remember to write all of those. Let me go ahead and delete this material here. The great thing is that we can just use the classes that are most important to us. So in this case, vertex shader code using the triple equals notation. This is a multi-line string. We need incoming data. So vertex 3, vertex position is the attribute created by sphere geometry. And again, we're going to use that position data when we generate the colors. So there's also going to be an out vec3. And I'll just call that position. Also, we expect to see uniform matrix 4s, 4x4 matrices, one called model matrix. Uniform mat 4, there should be a view matrix. And uniform mat 4, there should be a projection matrix. And the shader is not going to be too interesting. It's going to do the same things that the shaders normally do. It's going to use these matrices to calculate our new position. So just let me make a vec4 called pos. And that'll be a vec4 built out of vertex position combined with 1, that homogeneous fourth coordinate. And then, remember, one job to do for those vertex shaders, well, a minimum of one job, is to calculate GL position. That'll be projection matrix times view matrix times model matrix times pos. All right, and finally, I actually have to copy the value of vertex position into this outgoing variable position. So position equals vertex position. That's it for the vertex shader. Next, we need to write a fragment shader. Okay, so this will be, I'll call this FS code, a new multi-line string, triple quotation marks. We know there's an incoming vector 3 called position from the vertex shader. And there always has to be an outgoing vector 4, which transmits the color of the fragment. That's really all we need. Right? In this case, we can really streamline the shaders. We don't need to include vertex colors or any of these extra things we know we won't need. Let's write void main. And here, let's see, to compute the color, I can do this all in one line. Frag color is going to be vec4. Let me do this in 2 steps, actually. Vec3 color is going to be, I want to take the fractional part of the position. And then I'll build the frag color. And so then frag color will be a vec4 built from the RGB values of color and a 1 from the alpha component. That's it. That's our vertex shader. Again, fract is a GLSL function, which just gives us the fractional part of a number. All right, so there's our code. We have to use it to build a material. So material is a variable from the material class. It's going to use the vertex shader code and the fragment shader code that we just wrote. And one thing that the material classes always need to do is locate uniforms. Right. One thing you might be wondering about is, well, what about render settings? Do we really need to set any render settings? Right, so right now, the only render setting we really need, I'm looking at the material class now, is the draw style. And it turns out that we really very frequently are going to want to just render surfaces. So one thing I'd like to do is go back to the material class and make our life a little bit easier by setting a default render style of GL triangles. So again, going into the material class, right, that's material folder, material.py, from OpenGL.gl, import all the constants, import all the things. So let's add an import statement to material. And let's set this default, let's change that. Instead of none, let's use GL triangles. This will just make our lives a little bit easier. All right, so after locating the uniforms, there's really not much else to do. Right, the values of these three uniforms, those are set by the renderer. So we don't need to add any more uniforms to this material. I think we might be done. Let's try saving this and building it. See if there's any errors we need to squash. Hey, first try, that's looking pretty good. Just to see what it looks like all the way around, let's do a little bit of rotation too. Let's do self.mesh.rotate y by some small amount. Okay, let's build that one more time. There we go. Now you can really see the Z shading and the X shading. That's a really fun material. All right, that's one example of how you can create a custom material. I'd like to do one more example that showcases something different to create kind of an animated effect on a material. So again, it'll be kind of based on a sphere. Let's see, I have a slide of this as well. All right, the last example I'd like to do, I'd like to take a sphere and I'd like to do some displacement. Right, so here I'm changing the y coordinate of the sphere by some amount, and you can't see it in a still image, but I actually like to have kind of a rippling effect across the sphere. At the same time that it's rippling, right, the rippling of the positions, that will change in the Vertex Shader. I'd also like to animate some of the colors as well. So we'll add some animation and have it shift into a red color within the Fragment Shader. So let's make this cool animation. All right. So one more time, we're going to create a new example. So in our base folder, let's make a new file and save this one as test34d.py. And let's take all the code from test template. Let's copy it all and paste it all into that test file. All right, so lots of stuff to do here. The first thing, I need to import sphere again. So at the top of this file, let's add another import statement from geometry.spheregeometry, import sphere geometry. All right, now let's go down here. Again, we're going to create a nice large sphere geometry. And I want the radius to be 3. But I also want a lot of detail. I want a lot of vertices to make this look smooth. And since we're using the GPU, we can take advantage of that. Right, so for radius segments, that's when you go around the sphere, how many subdivisions to use. Let's use 128. And for height segments, let's see, that's just from top to bottom. So that's like halfway around. We can just use 64 for that. And again, in order to see the entire sphere at once, we're going to need to change the position of the camera. Let's go ahead and change that to a 7. Okay, so that's a great geometry. Let's delete the line of code where the material is created Once again, we're going to create a custom material. Right? Going to start off by writing our Vertex Shader and our Fragment Shader. So for the Vertex Shader, same stuff that we normally need. In vec3 vertex position. In vec3, in this case we're using vertex colors. So let's write the shader to support that. We need all of those uniform variables, so mat4 model matrix, uniform mat4 view matrix, and uniform mat4 projection matrix. And a couple more things we need. The color. Let's see. The vertex colors need to be sent from the vertex shader to the fragment shader. So we have an out vec3 for color. And also, to create an animated effect, we need something to change over time. So in this case, I will just pass in the time. Uniform float time. Okay, let's go ahead and write the void main. Let's see, so first I want to think about the offset. The offset is going to be in the y direction, but we saw the offset vary from left to right. So the offset will be applied to the y coordinate, but be calculated in terms of the x coordinate. And so some offset amount, not too much, so I'll say maybe 0.2 times sine of, I want lots of ripples, so maybe 8 times the vertex position dot x, because I want this to be applied along the x direction. And then we'll add time to that. So as time goes up, that's going to kind of shift the sine wave to the side. Right, once we have the offset, to create the position, right, of vec3, I'm going to start off setting that equal to vertex position plus, I'd like to add something to the y coordinate. So I can do that by saying adding a vec3 0, offset 0. All right, I can't add anything to vertex position directly. I can't change those values, so I copy that into a new variable. Set the value of GL position. As usual, that's the projection matrix times the view matrix times the model matrix times that new offset position. And, oh, it needs to be not just the position, but it needs to be, let me slip in a vec4 position, comma 1. And those are 4 by 4 matrices, so I need to multiply that by a vec4, homogeneous fourth coordinate. Cool. I also need to pass along the vertex colors to the vertex shader, or to the fragment shader. So color equals vertex color. I'll get nicely interpolated down there. All right, so there's our vertex shader. Next step is to write the fragment shader. So let's make a new variable. Let's call this FS code, fragment shader code. Let's see, in this case, what do we have? We have an incoming vec3. In vec3 color from the vertex shader. And also, I want to apply an effect over time that changes the color. So again, I'll reference uniform float time. Time does 2 different things here. And as always, I need an outgoing vec4. We'll call it frag color. And now let's write the shader, void main. All right, so I have time. Time is always increasing, but really, in this case, I'm going to have the color shift in terms of red. I wanted to shift from no red to tinted red and then back again. So I need to convert time to some value that oscillates between 0 and 1. One way I can do that, let's say create float, we'll call it R, make this the absolute value of sine of time. Right, so sine of time oscillates between 0 and, or sine oscillates between -1 and 1. Taking the absolute value makes it oscillate between 0 and 1. All right, I'll use this to build a reddish color. So vec4, let's call this color C. That'll be a vec4. Let's see, I want this to be red. And also, I'd like to take away some of the other colors, right? Because there's going to be some green and blue components in there as well. So I will do this sneaky thing. I will put a negative factor applied to R here. Right, so what's happening here? Oh, and this is a vec4, so I need a 0 at the end. Let's see. So, as the amount of red increases, I'm also going to decrease the amount of green and blue by adding these negative numbers in. Right, and now I can use this to build the frag color. Right, the frag color is going to be, well, whatever the color would have been, right, from the vertex color, plus this new kind of offset reddish color that we're adding to it. All right, that's the fragment shader. Now we use that to create a material. So material is equal to, let's create an instance of the material class, give it the vertex shader code and the fragment shader code. And in this case, we have defined a uniform that we need to add into the material. So material.addUniform. Let's say this is a float uniform called time. And we're going to start it off with the value 0. And then we need to locate all the uniforms. Not only this one that we added, but the matrices as well. And I also need some variable to keep track of time. We'll call that time. All right, that being said, we've got our material. We've got time. We create a mesh. We add it to the scene. Now, for the animation to work, in the update method, we need to change the value of time and then update the value stored in this uniform here. So now moving down to the update function, the first part's easy. Self.time plus equals, right, a 60th of a second has gone by. The slightly trickier part is how do we change the value stored in the material? Right, I could have made this a self.material, but we really don't need to because we have self.mesh. So I'll just go down through self.mesh. Each mesh contains a material. Each material contains a dictionary of uniforms. We want the one called time. That gives us a uniform object, and we want to change the data within it to be this new value of self.time. All right, let's give this a build. Let's see if this works. Hopefully we'll see a rippling effect, but we might not. Radius segments. Oh, I might have called that radial segments. Radial segments. Oh, something else. Radial segments also doesn't work. So for sphere geometry, what did we call that? Geometry, sphere geometry. Oh, we don't even have a way to pass that in. Let's see. In ellipsoid geometry? No, at no point did we actually define parameters to pass that in. Oops, let's just go ahead and change that right here. Let's make that 128 and 64. All right, so I'm increasing in the ellipsoid geometry class. I'm really raising the resolution here. All right, back to the test class. I mean, it would have worked even if we didn't set these values. Just, it wouldn't have been as smooth an effect. The more triangles you get, the smoother deformation you can see. So change is made to ellipsoid geometry, increasing the resolution along U and V. And then in the test class, now let's give that a try. All right, material object has no attribute, add uniform. Oh, did I not add this in yet? I might not have. Let's take a look. Under material. This is something I added when I was preparing this lesson because it makes life a lot easier. So within the material class, we often need to make uniform objects, but we might not want to always import the uniform class. So what I'd like to do is create a new function in the material class called add uniform. Right? And what do we need to create a uniform object? Well, we need to know what kind of data it's going to store. Right? So data type. We need to know what the name of the variable is going to be. So variable name. And then we need the actual data that's going to be stored in it. Right? So we're going to define this function here. And then, well, what do we want to do? Self.uniforms. Right? We're going to create a new entry in this dictionary with that variable name. And that's going to be a uniform with a given data type and whatever value data it has. And this is kind of parallels the structure, something we added in the geometry class. Right, in the geometry class, we have something similar. Oh, I need to add the self. I'll do that in a moment. In the geometry class, we have a simple way of adding attributes. So it kind of makes sense to add something similar for uniforms as well. And since this is an instance method, that first needs to be self. All right. So I'm glad we did that example, so we remembered to add this function. It really does make life a lot easier. All right, let's try building this class again. See how far we get this time. There we have it. That is pretty cool. And so you can see the ripples, right? The sine wave is being translated, so each one of these is slowly moving to the side. At the same time, the color is shifting from the original vertex colors to a shade of red. Right? It enhances the red that's already there and decreases the non-red parts. That's a fun shader. All right, we've done a lot of examples of custom geometries and custom materials. Hopefully this inspires you to create your own geometric shapes, to create your own materials. And in the next video, right, now that you know how to create these, there's a couple other mesh-like objects we should consider adding, and we should also consider making it easier to move around our screens. So in the next videos, we're going to talk about creating custom axis objects to help us orient ourselves, custom grid objects, and also a movement rate that'll help us move around the scene so we can appreciate it from all angles. That will be in the next video. Thanks for watching.